So now we come to GPT-2, right, where the idea was to see what happens, or one of the ideas was to see what happens when you're prompting large language models, right? So let's build the context for what all this means, right? So we have looked at three pre-trained or three large language models right now, right, which is BERT, GPT, and now BART, right? Now, in all of these cases, this is what you could do. You could have an original data set, like the entire Wikipedia, entire web, entire books corpus, your favorite data set, right? And we'll be covering data sets in much detail in a later lecture. But just think of all the data sets that any large scale text data set that you want to use. And then you're training these models, and all of these are in a self supervised manner. That means this data, you don't have any extra labels like, okay, this was the sentiment, or here's a question and here's the answer. It's just a set of sentences, and you corrupt certain things in the input and try to predict them back in the output, or you just keep predicting the next token as in GPT, right? So that's what you have done in pre-training. And now if you want to use this model for, say, sentiment analysis, right, then you will take a specific data for sentiment analysis, which would have positive and negative labels, and then you would feed this data to your model, whichever is your favorite model. And then what you will do is you will fine tune, right? So you can think of this process. I think we've done this in detail before, where you have this model, it has all the parameters, and now you want to predict plus minus based on the output. You want to predict 1 or 0. So you're adding some output layer here, and then you could choose to update all the parameters of the model using the training data that is available to you for that task, right? So this is task training data, and you'll update the parameters and you'll get some new parameters, right? So you could do this for the sentiment analysis task. Similarly, you could do this for other tasks of interest. And as I said, right, you back propagate. So you are taking the derivative of the loss function with respect to theta. Yeah, this probably this notation is a bit confusing. Maybe I'll change it. Yeah, so I just changed the notation. This is the derivative of the loss function with respect to theta. I think this is the form that we have been using in earlier material, so I'll just stick to that. Okay. And then you could take another task, which is, say, natural language inference. Again, you take this model, you are given some sentences, a pair of sentences, and you want to predict whether one sentence entails, contradicts, or has no relation to the other sentence, right? And again, you could have some training data for that task, and you could again update the weights using that training data and sort of get a new model, right? So this is the pre-training and fine-tuning stages that we have seen, right? And you make a new copy of the model for each task, right? Now, um, of course, fine-tuning a very large language model, right? And when you talk about modern language models, they are 7 billion, 3 billion, 1 billion parameters at the minimum, sort of, right? And then much larger models. So it is sort of, if you want to have to fine-tune it for every task of interest, that's going to be an expensive affair, right? And also you might need a lot of labels because it has a lot of parameters. If you want to update all the parameters, then you might need a lot of label data. Of course, there are other ways of dealing with that. You could use something known as adapters, which we'll hopefully see at some point, or you could just choose to like freeze most of the network and just train the output layer or so, right? But nonetheless, it's all expensive in whichever way you look at it, right? Whichever shortcut you choose, either it may be a bit suboptimal or it may be expensive, right? And more importantly, right, this whole point was that, hey, I've learned a lot about the language during pre-training, right? And that's the human analogy that, uh, say, for the first 10, 15 years of our life, we have learned quite a bit of language through interactions, formally, informally, right? In school, we would have studied language as a formal subject where we learn the rules of grammar, we learn vocabulary, we learn meanings, and so on. And through our daily conversations, of course, we are always learning language, right? And now, if you come and tell me after all of these, say, 10, 15 years of exposition to the language, if you tell even a kid that, hey, here's a paragraph, can you summarize it for me, right? The kid would understand what it means, right? And of course, you could debate whether the summary generated by the kid would be very good or not, but the task would be understood and a best effort summary would be generated, right? Without really sort of making the kid sit with you and say, like, here is a paragraph, this is what the summary looks like, and make him go through some thousand such examples. and then he understands, oh, this is what a summary means. It doesn't happen that way, right? You just prompt that, hey, can you summarize this? And based on his knowledge of what summarize means, based on his understanding of the paragraph that he's reading, he or she would be able to generate a summary. Right? So that's how humans work, right? We don't do this supervised fine tuning for every new task that we have to do. You would have never done a summary ever in your life before that, say, that point in time, right? But you still don't need to be shown 1,000 examples of what a good summary is. You'll just intuitively be able to do that, right? So we want the same thing to happen with large language models. Given that they have learned so much language, can we just make them learn a new task, and not just one task, but multiple such tasks with very few examples, ideally zero, right? So that's the idea that GPT-2 was trying to explore, right? And the idea was that without any explicit supervision, which is known as zero-shot transfer, right? So there are three. I mean, it's probably you'll hear this terms often in the context of LLM. So there is zero-shot, there is few-shot, and there is, I'll just call it full fine-tuning, right? So this is what we are used to so far, where I have a new task, I have some 10,000 labeled examples, and I sort of retrain the entire network using it. Entire network or a subset of parameters, just the last layer, all that, all those choices are there, but I'm going to like require label data at a very large scale and then try to learn, right? Few shot is where you say, okay, I have 10 to 50 examples, or even say 5 to 50 examples, and I'm going to try to learn a new task because I'm going to bank on this guy who has sort of learned a lot about language, and now maybe a few examples should get them there, right? And zero shot is like, I'm not even going to teach them what this task is. I'm never going to show them a summary, a paragraph and a summary. Just say that, hey, summarize this paragraph. That's zero shot transfer, right? So the idea that was explored in quite detail in the GPT-2 paper was that, can large language models be sort of unsupervised learners, right? So that's what we are trying to do right now, right? So we understand this is what we were doing so far. Now we are interested in this or this, right? So that's the idea that we're going to cover. Okay. Yes. So just using a simple tweak to the input, they did the following. So they said that, okay, so far what were we doing with the language model, right? And this is the GPT model. So this was like a causal language model. You're given a few input tokens, right? So you start a story once, oops, yeah, once upon a time there, and then you ask it to generate what comes after this, right? So this is what you are doing. So probability of an output sequence given some input tokens, right? That's the formulation that you had for a given single task, which was just next token prediction task, right? Now, can you do a very simple modification to this, right? And say that, okay, I'm going to give you an input sequence, and I'm also going to tell you what the task is, and then can you produce an output which is sort of makes sense given the task explanation that I've given to you, right? And we'll see what this means, right? So task is just an instruction in plain words, which is prepended or appended to the input, and then we expect the model to produce an output which of course is aware of what the input was as well as understands what the task is, right? So let's see what that means, right? And surprisingly, the model did quite well. So here's an example. You have the input text, I enjoyed watching the movie Transformers along with my dash dash dash, and you would have wanted it to complete the sequence, but now say you have given it the entire review or entire story that you want to say, right? You are saying something about what you did with the movie Transformers and so on, right? So, and now you give this task information, which is summarize or TLDR. TLDR is just too long, didn't read, so that means summarize. So this is the input that you're giving, right? So you have the input text, which was the paragraph that you wrote, and then you asked the model to summarize. So now you expect that when it starts generating tokens at the output, right, the next token prediction, it should generate something which is meaningful, right? And in this case, the only meaningful response is a summary of the entire input that you had given it, right? And maybe it generates a summary of something like this, that is, watch the Transformer movie, right? So that is what the summary of this entire story was, that I was going on and on about saying that I liked it, I did this, but the summary is that I watched the Transformer movie, right? And that's a crisp summary. So this is what we expect the model to do, that, hey, you've learned a lot about language. I'm not going to tell you do a supervised fine tuning where I'm going to compute gradients. Oops. Okay, I think, yeah. Where I'm going to compute gradients with respect to the loss and change theta to theta prime, right? Or a subset of thetas to theta prime. I'm not going to do all that, right? I'm just saying that, okay, you've learned a lot of language. Here's an input. Just generate an output which sort of is adheres to what is being said or obeys the input that is being given to you, right? So that's the idea. So they said that to do this, we need to scale up the model and the data, right? Because you're saying that you have taught me a lot about language, so you better give me a lot of data during pre-training and also give me a lot of capacity to learn, right? I'm currently a very small model. GPT was just 110 million parameters. Just give me a lot of capacity to learn, so make me a bigger model, right? So they increase the parameters to 10x, right? So they increased the number of layers to 4x. So from 12 layers, they went to 48 layers, right? And that resulted in the parameters becoming almost 10 times. So this was like a 1.5 billion parameter model. So this is the GPT model, GPT-2 model. Architecture wise, loss function wise, everything the same, right? There is no difference here. It's just like a larger on steroids model where you have more number of layers, and that of course results in more number of parameters, right? So that's the idea. That's a GPT-2 model. And of course, the other requirement was that you have to train me on much larger data, because you're saying that I have learned a lot about language. So please make sure that I indeed learn a lot about language. So that means what they did is they created a new, sort of crawled a new data set from Reddit, right? Which with a certain condition, right? Which had certain number of outbound links, and that they call the web text corpus, right? So this was a very large corpus, and it was ensured that this corpus is fairly diverse so that the model gets exposed to a lot of things and it has a good quality, right? So now what about translation tasks, right? So why am I asking this question? So I keep saying the models learn a lot about language, but maybe one language, right? So now I want this model to do everything, including translation. I should be able to say, here's an input sentence. So I just start writing something in English and then give it a prompt or a task which says translate the above to French, right? Will the model be able to do this also? Turns out that the data actually has a lot of such sequences also, right? So here's a thread which talks about, hey, this is what I wanted to say, and this is how I would say in French. And there are multiple such instances actually in the data set, right? So the model during its pre-training, right, just as a kid learns translation, right? So typically, at least in the context of India, most of us are bilingual. So we do learn these things where in a similar fashion, right? Someone would say that, okay, our parents or teachers, someone would teach us that if this is what you want to say, then this is how it would sound in Hindi, and this is how it would sound in English, and so on, right? So we do learn about these things also when we are learning language, and turns out that this large data set also had such instances. So maybe we can use it for translation tasks also. Maybe yes, maybe no, we'll see, right, whether it performs well or not, right? And this was about 8 million web pages, large in the context of the year in which this was published. But today, of course, this is much smaller than what modern large language models are trained on, right, in terms of the amount of data, right? So this was some 40 GB of data, 8 million web pages, and they used the BPE tokenizer, right? So as I said at the start of the lecture, although we looked at tokenizers in the context of BERT and decoding strategies in the context of GPT, these are interchangeable, right? So the same idea of using a tokenizer applies to GPT also. So they learned a tokenizer from this data. So it would have learned things like government perhaps gets split as govern and meant, because meant is a frequently occurring suffix, and govern, governs, governed, government, all of this governing, all of this govern appears quite frequently. So that should also be a character. So it would have emerged in the merge rules that we had, right? When we were pairing the tokens, okay? So that's the same thing that they would have done here and come up with a BP tokenizer. And the vocabulary that resulted, right, which was 50,257 tokens, right? So this is their vocabulary. And now this vocabulary has these tokens which are subword units. So it can represent unknown words and all the other things that we had seen in the previous lecture. Right? And this was the model, as I said. I'll just go over some more details. So they trained a family of models starting from 117 million, then 2x of that, then 2x of that, and then sort of 2x of that again, right? So they went from 12 layers to 24 to 36 to 48, right? And the D model, which is the dimension of the embedding, also was changed from 768 to 1024, 1280, 1600. So again, I'd like to make this point at this point, right? So if you have really understood the basic transformer architecture well, right, then all of this is just a piece of cake because you understand what I mean by D model, you understand what I mean by layers, you know how the parameters get computed based on the layers and D model, right? So all of this is fairly straightforward if you have really understood the transformer architecture well, right? So it's important to sort of get that drilled in so that you don't get stuck with these details when you're looking at newer large language models, right? The context window size was 1024, that means the sequence length, and the batch size was 512. So they would have 1024 sequence lengths and 512 such sequences in one batch, and the loss would be computed over this entire batch, right? And the training objective, as is the case with GPT, was causal language modeling, right? So nothing new here, right? Now we come to what were there as observations, right? And what they were interested in showing is, does this do well in zero shot, right? And why am I saying domain transfer? Because it has not been specifically trained on that domain slash task, right? And can it really do that task, right? So we have taken this pre-trained model. It has only been trained to predict the next tokens, but on a very, very large corpus, at least large in those years. Now we are going to look at its performance on a variety of tasks, right? So one of them being, so wiki data it has not seen. So now how does it do on the next token prediction task on wiki text, right? So they took some Wikipedia articles and you give it some initial sort of take a sentence from there, give it some initial words from the sentence, and how well does it predict the next sentence, right? So that's the task of language modeling. They also looked at the translation task, summarization task, and then reading comprehension, right? So what the names that you see here are all data sets for these different tasks, right? So you'll take the, you want to see what is the performance of, you'll take an instance from the wiki text data. So you'll take the starting point of some sentence from Wikipedia, and then you'll pass it to GPT-2 and you will see how well it is at generating it, right? Similarly, you'll take some paragraph and you will see how good it is as summarizing that paragraph. So all of this you're going to evaluate without explicitly teaching it that task, right? Now let's look at this plot here. So this is the language modeling task and we're calling it zero shot domain transfer because it has not seen Wikipedia kind of text in its data, right? All of its data was Reddit data. So if you look at this here, so they had the small model, remember the 110 parameters, then the 2x of that, then the 4x of that, and so on. So they tried all these models, and you can see what they compute here is something known as perplexity, right? For now, you could just think of it as a measure of how well it is able to predict the next token as compared to the expected token, right? So it's actually predicting a probability distribution at the output, if you remember, over the all the words in the vocabulary. So how good is this distribution compared to the actual distribution, which would have been like a peak at the correct word and zero everywhere, right? So this is the actual expected distribution and this is some distribution that it has predicted. So how close it is, right? That's roughly what they are trying to measure, and the lower the perplexity, the better it is doing, right? So you can see that as the model size increases from GPT to small to medium to large, the performance improves. And if you actually fine tune the model, right? We are evaluating the zero shot performance, but remember there was zero shot, few shot, and then there was full fine tuning. So this corresponds to full fine tuning. So if you fully fine tune the model, update its parameters to get a new theta dash, which is specifically trained for predicting Wikipedia kind of text or generating Wikipedia kind of text, then the model performance of course improves further, right? So that's the idea. But the zero shot performance, at least of the large model, is not very bad, right, compared to what you get with full fine tuning. Okay, so that's one task. Let's look at other tasks. So the next task they tried was character level language modeling. So this is another data set where you're trying to predict the next character given a sequence of characters, right? And here you measure it using something known as bits per character. All of these measures come from information theory, and this is again the similar thing that you try to measure how many bits you are going to send per character, right? And I'll try to do a lecture where I sort of focus on all these metrics, right? Sort of teach on what is perplexity, what is BPC, and all. But for now, you could just abstract it as it's trying to it's trying to measure how well it is predicting the next character, right? And again, GPT-2 performed quite well compared to whatever was the state of the art at that time, right? This is in 2019. Okay. So, and it has never been explicitly trained to do that. It has just been trained to predict the next token from some large corpus. This was a different uh, text from a different domain than what it had seen in the training data, and still it was able to do quite well on this. Then they looked at something known as closed task, right? So these are 10,000 passages from books corpus. So the input to the model is sort of like a snippet of a story, and the last sentence there is some word which has been hidden, and it has to predict that word correctly, right? So you can think of it as that the model is reading the entire sentence, and there is one word which is missing here, and the model has to output that correctly, right? So you can see that here you are measuring the accuracy. So the model is roughly 60 to 65% correctly being able to predict the word which is missing or which has been hidden in the passage, right? So again, just to repeat, you're given this entire passage, and the last sentence there's some word which is missing, and the job of the model is to predict that word, right? And it's able to do it quite accurately. Again, the important thing here is that the model has not been explicitly trained to do this task, and this is from the books corpus, which was not a part of the training data. So in all of these cases, right, whatever be the metric that you are measuring, right, the perplexity or BPC or accuracy, it was found that it was doing quite well without using any of these domain-specific training data sets. It has not seen any data from Wikipedia or from books corpus or anything, but it was still able to perform well on these tasks, right? So this was promising. It looked like it can actually learn a lot about the language, and then at test time it's just told that hey, do this, and it's able to do it quite well. And it of course was, its performance was far from SOTA, which is state of the art, when compared with models which are specifically fine tuned on those tasks, right? So that again we saw it in the first chart that I showed, that when GPT-2 was especially fine tuned for that task, the performance was much better, right? But still, it's promising results that without actually being trained on a specific task, just by scaling up the model as well as the data, it was able to perform quite well, right? And it still is not fully trained, right? So what this if you look at this loss curve here, it's showing that the model, if you increase the model size, it could have gone even further down, right? So it looks like you could do much better than just having a 1.5 billion parameter, and sort of this is where all the madness started, where we wanted to build bigger and bigger models, right? Because we realized that the current models are still being underfit. They don't have the capacity to even memorize what is there in the training data yet, right? And so create larger and larger data sets and then train bigger and bigger models on those data sets, right? And what it established is that large language models are unsupervised multitask learners. And this idea of prompting the model, right, saying that, hey, here's a text, I want a summary, can you generate the summary? Right? So it'll just generate it, right? So whatever we are used to today when we are I don't know in which year you are seeing this lecture, but sort of at least in 2024, we are used to talking to ChatGPT by just prompting it, right? We just say, here's a paragraph, sort of summarize it, or here's a question, can you answer it from this paragraph, and so on, right? So we are able to do all those things, and this was the early days where these ideas were being proposed, where you have trained a model, now you just need to prompt it and sort of get the tasks done, whichever task you are interested in. So now we'll stop here. So what we have done so far is we have looked at the BART model, then we have looked at GPT-2, and the main idea here, takeaway message here was that large language models are unsupervised multitask learners, right? And without being explicitly trained on a specific task, they were able to do quite well on that task, right? And again, BART is an encoder-decoder model, and GPT-2 is a decoder-only model. The reason we sort of, although the theme of this lecture was supposed to be encoder-decoder models, the reason we covered GPT-2 is to sort of go through this idea of a prompt and how, in an unsupervised manner, you can learn tasks, right? So I'll stop here, and then what we'll do going forward is start building towards the T5 model by asking a few questions and looking at the detailed study that the authors of the T5 model did to arrive at the final choices that they make for the T5 model.